we turn to our very last topic in mechanics, that of simple harmonic motion. Now, there are many objects and systems in the universe that undergo what we call periodic motion. And the idea of something undergoing periodic motion is that over some time period t, measured in seconds or whatever, the behavior of the system repeats in some way. So, obviously we could think of things like orbits. Over the period of the orbit, 1 year, they repeat. You might have the tides. We do a lot of things with springs and pendulums. Anything that goes back and forth. And this behavior can really look like a lot of different things. It could be something that's got a fairly chunky motion, like on, off. It could be a little bit more linear. But the thing that we are going to usually think of is this kind of sinusoidal motion, a sine or a cosine wave. And it's this and only this that we refer to as simple harmonic motion, or SHM. So although there's other forms of periodic motion, we're only going to be really talking about simple harmonic motion, about sinusoidal movement, so a sine or a cosine wave. Typically in this case, by the way, we are interested in the time period. And the time period t here is measured in cycles per second. No, excuse me. Not cycles per second. The time period t, is how long one cycle takes. It is seconds for one cycle. We will also sometimes talk about the frequency, which is measured in how many cycles do you get in 1 second, cycles per second. It's worth noting cycles per second is also referred to by the unit of hertz. And these have a perfectly reciprocal relationship where t is equal to the reciprocal of the frequency, and by the same note, frequency is the reciprocal of the time period. So for instance, a middle A, if you're a musician, a middle A resonates at 440 hertz. So that sound wave oscillates 440 times per second. That translates into a time period for each wave of about 2.27 milliseconds. So in this case, that sound wave for at middle A goes goes up and down, or makes one cycle every 2.2, like 2.25 milliseconds. So again, simple harmonic motion is specifically sines and cosines. So typically when we're looking at this, we'll look at a sine or a cosine. Now, a lot of times it turns out we actually want to look at the cosine. Not that this doesn't all work for sines also, but we're going to start by looking at the cosine here. And the reason we're going to start by looking at the cosine is a lot of times at time t equals 0, that's when the thing starts moving. We've taken a pendulum and we've offset it to some new position, some non-zero position, and then let it go so that it starts at an initial position, right? And in this case, we can write our equation this way. We can write it as x of t equals a cosine omega t. And this is our general, and it could have just as easily be a sine, but we're going to stick with cosine for the moment. And this is our general equation for simple harmonic motion for, and I'll even write it over here in our equation zone, omega t. And in this case, it's important to remember, as you probably know, the a refers to the amplitude. Of our wave, the maximum displacement. So it is worth noting, plus or minus a is going to be the max displacement. You might be wondering about this omega. The omega is what's called the angular frequency. Angular frequency, it is measured in radians per second, and it's defined here as being 2 pi over the time period, or 2 pi times f. And fortunately enough, that is on our equation sheet, but it still bears rewriting here. And what this is this relates the real world motion and the amount of time it takes to go through one cycle in the real world to the time that it takes to go through kind of the 2 pi radians of a full harmonic cycle. So yeah. Now we could find the velocity function here, and I'll switch my colors up. We could find the velocity function here just by taking a derivative. So I'd get negative a omega sine omega t. So in this case, we'd get something that would look like this for our velocity. So it's worth noting that the magnitude of the maximum velocity is a times omega. And when does the maximum speed occur? Well, the maximum speed occurs when we're at equilibrium, when our displacement is nothing. So, if we've got something on a spring, as it's passing through the middle is when it's going the fastest. So that comes up quite a lot. So let's take a quick example of what we can do with this, and then we're going to come back for a second half of the video where we're going to do a little bit of more complicated differential equations. So let's take a little example here. Give ourselves some workspace. And let's say that we've got a mass on a spring, right? So we've got a mass on a spring. And we're going to pull it 0.2 meters away from its equilibrium position, and we're going to let it go. And after we let it go, we're gonna watch it, and we're gonna find that it does that goes through 15 cycles, 15 full oscillations in 10 seconds. And just noting, a full cycle, right, goes from positive 0.2 to 0 to negative 0.2 to 0 and back to positive 0.2. And we want to ask ourselves a couple questions here. What is the time period and the frequency of this motion? What is the maximum speed of our object? And last but not least, if we can write the equation of our motion. So I'm going to actually give you a minute in PlayPosit to try these things. It does 15 cycles in 10 seconds. Can you figure out its time period, its maximum speed, and the equation of this? All right. So to find the time period, remembering that this is seconds for one cycle, well, we do 10 seconds for 15 cycles, which gives us 2/3, 0.67 seconds for one cycle. Notice that the reciprocal of this is the frequency, so this is 1.5 hertz. It makes 1.5 cycles every second. To find the maximum speed, you might be looking at this and saying, I have no idea what the maximum speed is. That seems rather difficult. But we remember that the maximum velocity for simple harmonic motion is our amplitude times omega. Our amplitude is 0.2 meters. And our omega here is going to be 2 pi times our frequency. Well, this is 3 pi. So we end up with 0.6 pi, which is, oh, I didn't actually calculate what 0.6 pi was, but in any case, it's 0.6 pi meters per second. I think that's like 1.88 maybe, something like that. And last but not least, can we write the equation? Well, now we have all the tools we need to write the equation. That the position of this thing as a function of time is going to be the amplitude times cosine And in this case, it's going to be 3 pi t. So we could use this equation to figure out at any point in the future where it is and how fast it's going. So we're going to take a moment now in our second half of our video, and we're going to do a little differential equations. We're going to do a little bit of calculus magic, and we're going to actually figure out a little bit more about two specific scenarios for simple harmonic motion, specifically those of springs and pendulums. So take it away. So it turns out that we can use some of the tools we already have in physics and calculus to do a little bit more of an in-depth look at two particular systems, springs and pendulums. So we're going to start with springs. So imagine that I put a mass m attach it to a spring of spring constant k, and I'm going to pull it back some distance and let it go. And what's going to happen is it's going to go, it's going to bounce back and forth on the spring. And I want to be able to analyze that motion. So I want to note that we know about the force from a spring. We know that the force from a spring is equal to negative kx. And I've kind of heretofore in class sort of ignored the minus sign or explained it away as, well, that's okay. It just tells you that it wants to, it tells you the direction of the force. But here in this case, it's actually really important. It's really important because I want you to note, if I have x to the right being positive, when x is positive, our force is in the negative direction. And when x is negative, our force is in the positive direction. This is, by the way, for those of you who like this kind of thing, this is what's known in physics as a restoring force. In any case, because it tries to bring you back to equilibrium. In any case, that minus turns out to be very important here. So I'm going to do a little bit of calculus, and I'm going to remind us that we know that forces are equal to ma. F equals ma. But that we know that acceleration is actually something special. Acceleration is the second derivative of position. And I'm actually going to rewrite this in a way, because I love physics, that you'll actually see it in a lot of physics textbooks. You might see it with the second derivative. You also might see it this way, with x double dot negative k over mx. This is very important. First of all, what does the dot mean? For those of you I threw, this is not suddenly a heavy metal album. The dot just means a derivative specifically in physics with respect to time. So if it's a derivative with respect to something else, we don't use a dot. This means the second derivative, of x specifically with respect to time. But it tells us the second derivative of x with respect to time is equal to negative k over m times the original function x. And this is, of course, a differential equation, which is just a fancy word for an equation with a derivative in it. But it's asking us a question. It's saying, you could find the exact motion, x of t, of this mass on a spring, if you can find a function x such that the second derivative of x is equal to negative some constant times x. So here's the point in math where we'd have to rack our brain and try to say, well, what's a function when I take two derivatives? I end up with something that's kind of like the original function, but negative. And after a little bit of searching, you might guess, this is the simple harmonic motion unit, or from your experience with calculus, you might guess, what if we try a sine or a cosine function? So in this case, we're going to try cosine. What if I try x of t equals a cosine omega t? Well, in that case, my first derivative is negative a omega sine omega t. And my second derivative is negative a omega squared cosine omega t. Notice that this is just negative omega squared times a cosine omega t, which was our original function. So we've actually found a solution to this differential equation. And specifically, this is a solution to the differential equation where we found that x is going to be a cosine omega t, but specifically, notice that we have to have omega squared equal to k over m, or in this case, omega equals root k over m. And therefore, the time period for a spring is 2 pi root m over k. And this is so important that I'm actually going to go write it in the important equation zone, and then we're going to talk about it. So for a spring, the omega for a spring is root k over m, and the time period for a spring is 2 pi root m over k. Why is this so important? Well, first of all, we've just found some important things about springs, and certainly we'll use these equations a whole lot. The thing that I really want to drive home, and the reason why differential equations are awesome in physics, it's not just because they're hard and they're calculus magic or whatever. Why are differential equations great? And the reason differential equations are great is that any equation that looks like this is simple harmonic motion. Any equation that looks like the second derivative of some function equals like negative some number times the original function, no matter what it is, you know right away that it's simple harmonic motion. And that's a really powerful thought. Just by getting a particular equation, a particular differential equation, you know immediately how the system behaves. And why is that important? Well, we're going to see in a moment another system that obeys simple harmonic motion as well. So I'm going to throw up a quick little example problem on the screen in just a moment for springs. So take a moment, and then we're going to do some pendulums. By the way, if you were doing that example problem, you should have gotten k equals like about 30.84 for that. All right, I want to turn my attention now to pendulums. So let's make a nice bright line here. Great, to pendulums. Let's talk about pendulums. So a pendulum, you may have seen them, right? It's got like a little, the pendulum we're going to deal with here is a little bob of mass m. We're going to put it on the end of a string of length L, and we're just going to let it swing back and forth. And it is periodic. It goes back and forth and back and forth and back and forth. And the idea is that we want to figure out its motion. Now in this case, rather than using F equals ma, we're actually going to do a similar thing, but we're going to use torque equals I alpha. And in this case, we're going to assume that the string is massless. All we're dealing with is the little bob at the end. So where does the torque come from? The torque comes from gravity. So we can go ahead and work this out real quick. If this is theta, so is this. So the torque here is going to be mg times the length L times the sine of theta. And that's going to equal I alpha. And the I here is just ml squared alpha. Before I move on, I do want to do one important thing, which is to put a minus side on the left side here. Why am I putting a minus side on the left side here? Well, again, look at what this torque is doing. Let's say this way is my positive direction for my angle for theta. If I make my angle theta positive, my torque is in the negative direction. If I make my angle theta negative, my torque is in the positive direction. So the torque is always pushing in a particular direction. So I'm going to do a little bit of cancellation here. My m's go away, as it turns out. The mass of the bob doesn't matter. One of my l's goes away. And I end up with an equation that looks like this. Alpha, and I'm just going to rewrite alpha as, eventually, as theta double dot. Wow. That's, come on, pen. As theta double dot equals me changing colors midstream equals negative g over L sine theta. So theta double dot equals negative g over L sine theta. And here's where we get to a problem. This equation does not look like this equation or this equation. There's a tricky sine theta in here. And this actually is even worse than you might expect. This is an equation that cannot be solved. And I don't mean it's hard to solve. I don't mean that it's a little inconvenient or beyond the scope of this class. This equation has no solution, has no closed solution. You cannot write down an equation for theta of t that satisfies this equation because it runs into something called elliptic integrals. This is actually an impossible problem. And that's kind of a shocking thing to hear, I think, sometimes in a high school physics class. We're very used to being able to do all of this math and get these perfect answers. And I think this is a really important lesson that once you step outside of the carefully manicured garden of like perfectly lovely classroom solutions, most of the real world is like this. Most of physics, most of engineering is like this, where there's no perfect solution. There's no exact solution. But we don't give up. Is the important thing. And as a scientist, as an engineer, as a physicist, if you can't get a perfect solution, what you get is a pretty good solution. So what we're going to do is we are going to approximate. If we look at the function y equals sine x, it looks right around 0. It looks like this. And in fact, if I get quite close to 0, it looks pretty straight. And so I'm going to ask this question, what if I just assume it is straight? Very, very, very close to the origin, y equals sine x looks a lot like y equals x. And in fact, you can graph them yourself and zoom in. We can make a pretty good assumption that as long as x is small, if x is small, sine x is approximately equal to just x. Now, again, this might strike you as ridiculous. How small is small? Well, it turns out that as long as your angle is less than about 15 degrees, 15 to 20 degrees, this is a pretty darn good approximation. Your error is very small. So how good is good? As long as your angle is not too big, it's quite good, and it provides a useful result. And I'm just going to point out, for those of you who are more calculus-y, you can always, if this is bothering you, you can always remind yourself of the fact that this really represents just the first order term of the full Taylor series expansion for sine. We're just not worrying about the rest of it, and we're focusing on x. And if we do that, what happens is this equation becomes theta double dot is more or less equal to negative g over L times theta. Aha! Simple harmonic motion. So what we conclude is that a pendulum for small angles, and this is in fact called specifically the small angle approximation. For small angles, theta moves as simple harmonic motion in theta with an omega that's equal to root g over L, or a time period that's equal to 2 pi root L over g. And again, I'm going to go ahead and write these in here, that the omega for a pendulum is root g over L, and that the time period for a pendulum is 2 pi root L over g. And again, is that totally true? No. Is it good enough for clockmakers and all kinds of other physicists and engineers to use pendulums and assume that they're simple harmonic motion as long as their angle doesn't get too big? Absolutely. So this is a really important lesson moving forward in physics and engineering. You're going to see a lot more approximations, my friend, as you go on, because it turns out the real world is extremely complicated and does not provide us, does not neatly dish up clean answers. In any case, armed with all of these equations, we are now going to delve into a bunch of practice on simple harmonic motion.